Okay, we're designing a poster, but when you print stuff out of your printer, or when you print stuff out of those big printers, there's always a margin, right? So here's our paper. The printer can't reach the very edges. I guess with the more modern ones they can. So this question's a little outdated probably. Um, no, most of the ones at houses can't do this right now. They can't print right to the edge, but there's plenty of printers out there. We got 3D printers making houses for Pete's sakes. But what they're saying is there's a 3-inch margin it can't print on the top and the bottom, and there's a 2-inch margin on each side that it can't print on. But they said, well, yeah, we got those margins, but it's supposed to have 60 square inches of printing. So all this area on the inside, outside, away from the margins, the printing area needs to be 60 square inches. Okay, so the problem is we don't know the overall dimensions. We don't know how big this is, and we don't know how big this is. So we'll call this big distance that we're trying to solve for, we'll call that y, and we'll call this big distance x. Okay. So we want to know what x and y are so that we have 60 square inches in here. So we need to come up with separate expressions for the actual printing area because it's a little bit different. So this isn't x all the way across, right? Because we lost 2 inches here and we lost 2 inches here. So this part of the area is whatever x is subtracted by 4 because of the dimensions we lost over here. And then this is 3 inches, this is 3 inches, so this printing area has y minus 6 inches available. And so the printing area is just length times width. It's just a little bit more complicated. The area of the printing is the length, x minus 4, times the width, y minus 6. Okay. Um, okay, we want to minimize the amount of paper used. Okay, so I see what we're doing. So they tell us something about the printing area. This red area that I'm shading here, I went a little outside actually. Let's try that again. This red area is 60 inches. So we can plug in 60 for the area, and then we still have two variables, right? So that's nothing we can solve or take a derivative of, but that's going to help us because our goal is to minimize this bigger area, this entire paper, right? We want to waste less product, but still have 60 square inches inside here. So we'll call that area sub 1, and then this will be area sub 2. Okay. The big area is x times y, and that's what we're trying to minimize. So if we can somehow solve for x or for y in this equation, we can plug it in here and then do some calculus magic to find out the right dimensions. So can you solve for x or y here? I don't know. Yes, you can. Okay. What you'll want to do is pick one. It doesn't matter in this case. I'll solve for x, so I'm going to divide y minus 6 from both sides. Okay. And I gotta move this. So I'll recreate this in just a bit. I need to plug in an X or a Y into that area for the bigger, the whole amount of paper. So that's 60 over Y minus 6 equals X minus 4 because I made this cancel out, right? So you want to add that 4 to both sides to finish getting X by itself. So this is what X is equal to. Okay. So with the bigger area, the entire paper, margins and printing area all together, we said that's x times y for the area. But now that we have an expression for x, we can plug that in and make it all in terms of y. That way we can take a derivative, set it equal to 0 to help us try to maximize it. Okay, so it's going to be in terms of y, but we can still do our calculus magic with it. So this is our area. I'm going to distribute that y to help us simplify a little bit. Y times this term, I'll just put it up top, 60y, because it can't cancel with that y on bottom. And then y times 4 makes 4y. So that's our function for the area in terms of just y. So we want to take a derivative and set it equal to 0 to try to maximize it. So this derivative needs the quotient rule. It's a derivative of the top function times the bottom function kept the same, plus the top function kept the same times a derivative of the bottom function, all over the bottom function squared. Okay? And then the next one, taking a derivative of 4y, that's just 4. So there's our derivative. If we distribute, oh, I messed up the quotient rule. It's supposed to be subtract. Oh man, what a bad teacher. Sorry about that. The quotient rule is the derivative of the top function times the bottom function kept the same, subtracted by the top function kept the same times the derivative of the bottom. I put a plus there. I'm sorry. That's our derivative. We're going to set it equal to 0. And while I do that, I'll distribute. This is 60y minus 360 minus 60y all over y minus 6 squared plus 4. So look, 60y minus 60y, that cancels out. So it makes a negative 360 on the top. But we're trying to set this equal to 0 so that we can find potential maxes or mins, the critical points. But we always want to remember, critical points happen where the derivative fails to exist. At y equals 6, we have a divide by 0 error. So that's a possible max or min. But if we actually have y equals 6, then 6 minus 6 makes 0, and then we have 0 for printing area, because 0 times whatever this is going to be 0. So that's no good. So we can forget about that one. To solve for y in the denominator, you want to multiply both sides of the equation by y minus 6 squared, okay? Because that times 0 makes 0. That times this term gets it out of the denominator. They cancel out with one another. And then y minus 6 squared times 4 is 4 times y minus 6 squared. Okay. And then we just have to finish solving that equation. I ran out of room on my whiteboard, but we'll add that 360 to both sides to make it cancel out. And that 4 is multiplying to this parentheses, right? So divide 4 from both sides. That's 90 on the left. So to solve for a square, I'm going to take a square root. And I want to consider both positive and negative usually. But we don't care about negative answers. Actually, it still might turn out to be positive. So positive or negative, every time you use a square root to cancel out a squared. And then we want to add 6 to both sides. So we have two critical points. Square root of positive or negative square root of 90 plus 6 equals y. Okay, so let's check those. I don't know what the square root of 90 is off the top of my head. Oh, but that's not going to be, that's going to be negative. So it's probably not worth it, but I'll just show you. Square root of 90 negative plus 6, that gives us a negative y, which we don't care about, right? So we only want to consider the positive and add 6 to this. That's 15.49. So it's 15.49 for y. Okay, that's our value for y. That maximizes it. Let me check with my book sometimes. No. Oh, I made this up. Okay, phew. I was looking at the book's answer, but I realized I made this question up. That's why it's a decimal. So that's the y dimension. That's this part over here. To find out the x dimension, you just plug this into any equation that has x. You could plug it in here, or no, you got to plug it in this one. So you plug in y, 15.49. Subtract that by 6. So 9.49. So 60 divided by 9.49 plus 4. That's 10.32 for x. Okay, those are the dimensions that minimize the amount of paper used. And I actually took something for granted. I took the derivative, set it equal to 0, and solved. What you'd want to do is check y equals 15 and check y equals 16 and make sure that's a minimum. But you can be assured that that's a minimum because if you just graph this expression, which is, graph this expression, you'll see that around 15.49 it's at its lowest point. So I graphed it for you in Desmos, and you can't have a negative value for y, so that doesn't make sense. So it looks like it's not even here, but you just got to scroll up. Okay, there's our minimum at 15.47. So took a derivative, set it equals 0. Desmos confirmed that yes, that was a minimum.